Aloha and welcome to the regression forecasting and modeling screencast. We're going to talk about a process to use regression for forecasting revenues and finding a good model and validating that model. So you're probably going to want to get the presentation slides here. Generally, we're just going to follow what's presented in these slides. So you can have these handy and you can go through them. We're also going to use the AFM FP1 FP2 example. We're going to build on that. So it's kind of assuming it's like your FP1 and FP2 for your project are already done, and we're going to see how to take that essentially to an FP3. Everything that we're talking about in this screencast will be detailed in the Almost Family Forecasting Project spreadsheet. So this is a spreadsheet with a bunch of notes, and it's kind of detailing what we're going through here. But I encourage you to go get this one, download that, and follow along with me. You'll probably be better off following along with this and stopping. So it looks like this. This is the AFM, Almost Family Home, FP1 and FP2, and you can see that it just is quarterly revenue up to 2002 quarter two, and has forecasts for a bunch of different drivers, which perhaps you got from FP2. And it has some analysis of the seasonality and the correlation, again, from FP1 and FP2. So you should probably have this handy, and I would encourage you to follow along with me and see if you can get the same results, just so you get a feel for how this works. It can be a little confusing. This is going to be the outline that we'll more or less follow. So let's get started. So the situation is that we have a potentially large set of predictor variables to predict revenue from past 7 years of revenue data. And what we want to do is find a model that explains that revenue with a small set of predictors, rather than looking at all of them at once. We want to kind of pare them down to sort of a best set. And there's a good reason for this. Not only is the model easier to work with, and it'll require less data, there's always the problem of sort of overfitting, and that you're using too many predictors to get your data. And also it makes it less reliable because those predictors also have to have forecasts, and those introduce additional errors. So you kind of want to get away with as few as you can, but you don't want to have too few that you're not getting good predictions. One of the problems with having a lot of predictors, of course, is that, if I call it the friend of the friend is your friend problem. So if I am really good friends with somebody and you're really good friends with somebody, it's not uncommon for you and I also to be really good friends. So when the independent variables have too much relationship to each other, they can cause problems, because what happens is, just like with the friend that we're both friends with, we may be competing for that friend's attention. And so in regression, independent variables that are too correlated to each other will actually compete for fitting the data to the dependent variable. And that throws things off. It makes things less significant and makes it a little difficult to work with. And of course, we're going to use the revenue data that's either seasonally adjusted or not seasonally adjusted, depending on whether we see evidence of seasonality. And that's used to reduce variability, because if it varies by quarter, the revenue, then that's going to add an extra degree of variability that's not going to be explainable by the model. And so we try to smooth that out by seasonally adjusting it. And then, of course, what we do is when we make our predictions, we adjust it back. And that just helps us make better predictions. So the first thing to think about is that when we speculate on which predictors are going to be good for our model, it's not uncommon for them to be related. And if they are indeed too related, we get this problem of multicollinearity. So how do you find multicollinearity? What we're going to do is we'll start by looking at the correlation matrix, just like we did in FP2. And then we will look at the variance inflation factors and try to understand which ones we might be able to drop. But we start with the correlation matrix to give us an idea right off the bat which things are going to be too correlated. And so when we get the VIF values to tell us which ones we might want to drop, we can have some choice in which one we drop. We can try to drop the one that's going to give us the least benefit, or maybe fixes some problems we have. So let's do that. Let's just start with that. Let's go back to this. And so we're here over at our data for Almost Family Home, and this is what we want to predict. I'm just going to color code those. Remember, these are all presumably forecasted values. I know that it's past quarter. I know that we're not in, we're way past quarter 3, 2012, but we're just going to kind of go back in history and assume we don't have this data, and that's what we want to forecast, and that these were forecasted values. We have a large number of drivers here that we have some reason to believe are related. And the first thing to do is take a look at our seasonality. And from FP1, we see that seasonality isn't an issue, at least in terms of the indices here. But what we do want to take note of is that even though we're going to use non-seasonally adjusted data, because of the indices are not indicating that there's seasonality, we also take a look at the trend here, and we see that that there are potential modes that we might want to look at that could cause us some problems later. And I noticed that there's a good number of them, about 10 here, that are below the trend line, and here's more than 10 above the trend line, and then it goes back down. So normally what we'd expect is normal variation. We kind of see it going up and down and up and down and up and down and up and down. But what happened is that there's something happening over time, like over at this thing, that sort of started making the revenue go up and then stay up, and then something had happened over here that made it go down. Now, we may or may not be able to determine what that is, but we're just going to kind of make a note of it right now, just like we did in the Southwest Airlines example, where there was an acquisition by Southwest Airlines of AirTran, and that popped the revenue way up. So we may need to go back to that later if we are having some problems explaining the variability with our model, with our particular drivers. So we go now look at our correlation matrix, and the correlation matrix from FP2 shows us that we do indeed have a number of things that are strongly correlated to our revenues. So, these are good candidates. Things with 0.9, 0.8, very good candidates for things that are likely to be useful in predicting revenues. Essentially, when you do the correlation matrix, you're doing the regression. It's just not fitting it to a particular model. But this is definitely going to show that there's some prediction power here. And you can see some ones that are potentially not useful, like gross domestic product here. Real RDP is not so good, and retail price of gasoline is not so good. You also notice that some things are yellow and some things are not yellow. The ones that are not yellow are not significant according to the either 0.05 level of significance or the 0.01 level of significance. So, of course, whenever you see critical values or p-values, it's going to tell you that there's a hypothesis behind it. And the hypothesis here is that the correlation coefficient is 0 or not 0. So when you don't have it yellow, we are not necessarily confident that the correlation coefficient between these two variables is not 0. So it may very well be 0. So that lends some doubt on to whether that's a useful predictor. So the yellow here is simply just tells us whether it's significant or not significant. And there's two levels of yellow. We have the 0.05, which is kind of light yellow, and the dark yellow at 0.01. We just need to be confident enough. Again, it's not really a big deal if it's that much more confident. Typically, values that are very close to zero 0.9 and stuff like that are going to be significant, but it all depends on the variability in the data. So it's possible to have a high correlation that's not significant, high estimate of the correlation that's not significant. Because remember, these are all estimated data on the data. Really what we want to watch out for, of course, are the things that are 0.9 and above. Not for revenues, that's our dependent variable, but for all the independent variables, because of multicollinearity issues, we're going to look for things that are 0.9 and above, because those will almost surely cause VIF problems. And so we'll just go through this really quickly and just sort of mark them in orange so we don't see any 0.9s or above here. We do see something that's kind of high. That could be a problem. There's another kind of high one, but still less than 0.9. Looking down here, here's one that's over 0.9, so we'll make that orange. Tell you what, we'll make it salmon just to make it a little easier to read. And going down the list, that's okay, and that's okay, and that's not okay, and that's not okay. And we've got one over here. That's not okay. And I think that's good. So these are the ones that we're going to keep an eye on. In other words, we have population highly correlated with consumer price index, population 65 plus correlated with medical quarterly allowed expenditures. And as a result, if we're going to have to drop one of these because of high VIF, then we can drop one or the other. Because essentially they're both providing the same information, and that's not necessarily going to help us. So we have a choice to drop the one that we think is better for one reason or another, or not better, sorry, drop the one that's not better for us, keep the one that's better. Okay, so what we want to do is start looking at the variance inflation factors. So again, it's a measure of how highly correlated each independent variable is with the other predictors in the model. So when the Megastat calculates the VIF, it actually doesn't look at the dependent variable, which is revenues, at all. It starts looking at how each independent variable can be predicted by the other independent variables. And if it looks like that you have significant fit, meaning like R squared, then the VIF will be high. So literally the VIF is actually kind of the inverse of the R squared when you fit the independent variable that you're looking at with all the other independent variables. So never mind the technicalities. The upshot of it is high VIF values are bad because low values of R squared are bad. And if you divide by something that's small, you get a very large number. And that's all we have to worry about. So the rule of thumb is that anything larger than 10 is a problem in terms of the inflation of the standard errors and also competition for the significance of the slopes. So we do need to get that kind of out of the way right off the bat. So the way we do it is we run a regression, and we're also going to keep an eye on our Durbin-Watson because it's quite common as we drop out values that are that have high correlation that will start to get autocorrelation, things that are correlated with itself, and that causes a different kind of problem. And we're going to basically delete one variable at a time until we get all VIFs less than 10. Once again, when we delete or remove the variables that have high VIF, we'll have some choice in which one. We may look at one that's highly correlated with another one, and for some reason or another, we prefer to keep the one with the high VIF and drop the one that it's highly correlated with instead, possibly because the one that we're dropping has other problems. It's not as good, or in terms of its correlation with the dependent variable or revenues, or it has some nonlinearity problems or some other assumption problems. So we keep doing this until we get all VIFs less than 10. So let's go ahead and get started on this. So we go to our data here, and we simply go to Megastat, correlation regression, regression analysis, And we don't really need a whole lot here. So we're going to take our independent variables. Whoops. Let's move this. It's kind of hard to figure out where to put this. Let's put that over there. So we want our independent variables. That's all over here. Notice we only want the data, not the forecasts. And then we get our dependent variable, which is revenues in millions. Again, just the data. And we do want the variance inflation factors. We don't really need that. We do want to get the Durbin-Watson and go ahead and get the Cook's D, even though we don't actually need it right now. But we're going to keep an eye on whether we get outliers, and that might help us decide what variables to drop if we're getting outliers. And that's all we need to do. We don't need to make any predictions at this point, because we're really mostly interested in the VIFs here. So I'm going to take a note that we do have a high adjusted R squared. That's quite good. That means that out of this set of drivers, there's probably a subset that's going to give us a very good model in terms of adjusted R squared. So we may not be able to achieve 0.989, but we should be able to get over 0.9 by dropping things and getting a good model that meets all the assumptions. Well, sure enough, as expected, we have some pretty darn high VIFs. We have this one over here at 323. And that's not unexpected because we had some very high correlations in the correlation matrix. So we're going to start by taking a look. We're not even going to bother looking at any of this. I do know notice the Durbin-Watson's 1.7, and we want to keep that above 1.3 if possible. So I see the consumer price index is the highest, and you notice that Megastat kind of makes these things yellow. It's kind of giving you the two things it thinks might be problematic, that this is interacting with this one here. But we're just going to take a look at the very first highest VIF one, consumer price index, and see what happens if we drop that. But before we do that, let's go see if there's another thing that might be better to drop that it's correlated with. I can guarantee that it's highly correlated with one of these other ones. So I'm going to go over to here and I'm going to look at consumer price index. There it is. And I see it has a pretty good correlation with our dependent variable revenues. That's good. We do want that to be high. Here's where we want it to be low, and 0.543 is pretty high, but not too high. That's getting up there and pushing it. Oops, population 65 plus, that's over 0.9. That's probably the problem. Here's another one. Here's another one. It's okay. That's okay. So we conceivably could drop either consumer price index or population 65 plus. Looking at population 65 plus, I see that its correlation with revenues is 0.946, which is quite a bit higher than consumer price index. So if I have to, I'd rather keep population 65 plus over consumer price index because it has a better correlation with revenue. So it's going to give us a better model if we keep that in there. So I don't have any reason not to drop consumer price index because the thing that is correlated with is actually better to keep in there. So I'll go ahead and drop consumer price index, and I don't really at this point have any other reason why I'd want to keep consumer price index. So I take consumer price index, which is right here, and I'm just gonna cut it, and I'm gonna move it over to the side here. I don't want to get rid of it entirely because I may want to put it back in later, and maybe I'll take out population 65 plus if I find that there's a problem with my model. So I go ahead and go to Megastat and I rerun the regression. And all I need to do is just change the independent variable because I have one less column. So I'll just go ahead and I can either type that in by hand or be careful and select all those things, and I rerun the regression. And I notice that I still have my R squared just 986 still good, and I notice a considerable improvement in the VIS, but they are still, many of them above 10, so I still got a problem. And I'm noticing that my Durbin-Watson dropped itself down to 1.32. Still okay, but getting kind of close, so I should probably be careful from here on out. So my next highest VIF is the population 65 plus. Not a big surprise there. So once again, let's go take a look at that. So I look at population 65 plus, and I'm noticing that here's population 65 plus, and I already dropped consumer price index here, but I also see it's highly correlated with Medicare quarterly allowed expenditures. Now, that has a correlation of 0.901. This has a correlation of 0.946. It may be a good idea for me to drop out Medicare quarterly allowed expenditures. They're not really that much different. They're both above 0.9. They're both quite good. So, it's neither here nor there at the moment. I do notice that Medicare quarterly expenditures also seems to have, look, I'm looking at the correlations for the other things. It has a high correlation with the consumer price index, which I dropped, so that's gone. But prime lending rate is bad. Well, not bad, but it's pushing it. And looking at population 65 plus, I see it's over there. So it's really kind of a toss-up, I'm going to go ahead and just drop population 65 plus, although I probably could just go ahead and drop Medicare quarterly allowed expenditures and do just as well. But let's go ahead and drop 65 plus and see what happens there. Take that, cut that. And again, I keep in mind that I can always put it back if I have problems later. Okay, going to Megastat, correlation regression analysis. I think what I'm going to do is I'm just going to take this and change it from K to J. I'm just going to go down, from K. Oh, okay, that did not work. Let's try just selecting it there, rerunning it. Thought I'd save some time, but I didn't. Getting some improvements in the VIFs. Durbin-Watson actually went up. That's good. So maybe I made the right choice by dropping population 65 plus and not the Medicare expenditures. But of course, if you want to, you can go try it out and see what happens, dropping Medicare expenditures instead. But it seems to have worked okay. 9.984 R-squared, still pretty good. And but I still have some high VIFs, and it looks like unemployment rate is my next candidate. So once again, I go to my correlation and I look at unemployment. Okay, here's unemployment. And I don't really see anything that it's highly correlated with, so I don't really see a big swap out. Perhaps population 65 plus, but I already dropped that. So unemployment itself has a pretty high correlation, 0.944. Alrighty, so what to do? Let's just drop it out and see what happens. So again, there's a kind of a fair degree of fiddling around and kind of keeping open mind, but what to do here. It's not really a set process. Okay. One more round. Here we go. And now we see a considerably good drop in the VIFs. They're all getting darn close to 10 or under 10. I see my Durbin-Watson dropped out, so down a little bit, but still okay. So I'm still in the clear here. And I didn't really have anything else to swap it out with anyways. So we're going to take a look at the next candidate here. And I could just go ahead and see what happens with this because this is pretty close, but let's just go one more step to make this even easier. I see my biggest one is U.S. prime lending right now. We do need to be careful here that, we're really get into that territory where it's not so significant. The VIF is high, but we'll probably be able to get that down to a reasonable level by just looking at the best model. You'll see what I'm talking about later. But as we think about what to drop here, it's not necessarily the case that I'm going to want to drop the highest VIF, because look at this, it's 11.395. It's not much different than that, and it's not much different than that. They're all pretty close. So actually, all of these are good candidates to drop. Gross domestic product, U.S. prime lending rate, or quarterly allowed expenditure. So I'm going to go take a look at my correlations and with revenue to see which one gives me the weakest correlation with our dependent variable or revenues, and I'm going to drop that one because, again, it doesn't look like any of these are significantly different in terms of their multicollinearity with the other things. So I might as well go ahead and keep the ones that are going to give us the strongest model. So, let me make a note of that. So we're looking at prime lending rate, monthly quarterly expenditures, and real gross domestic product. So looking at real gross domestic product, I see it has a pretty miserable correlation with revenues, 0.168, not even significant. That's not going to really contribute much to my model, so that's a good candidate to drop. Then I have the prime lending rate at minus 0.96, very strong, and monthly quarterly allowed expenditures, very strong. So those are probably better to keep in there. Let's just take a look at the highest VF one anyways was U.S. prime lending rate. Let's just see if there's anything that I could swap it out with. So here's prime lending rate, and indeed I can drop it out with unemployment rate, but I already took out, I could swap it out with unemployment rate, but I already took out unemployment rate, so that's just not available to us. So I am for the reason that this one has the real gross domestic product has the very, very low, if not insignificant correlation with our dependent variable. Because this is low, I'm going to just drop this one out because these ones are better candidates overall. And again, the VIFs were not that much different for all of these. So if I had a choice, this is probably the better choice. So it's not always going with the highest one, just to let you know. So going to data here, and I'm going to take out real gross domestic product. Okay, cut that, put that over here, ping, and then I delete that and go back to Megastat, and I'm pretty sure I'm going to be okay at this point, multicollinearity wise. Okay, got that there, and this time what I'm going to do is, because I'm pretty sure I'm okay, I'm going to go ahead and no. I'll let this go. Yeah. Let's just make sure it's okay. Okay, there we go. So as expected, they're all below 10. Notice I still have a high adjusted R squared, 0.966, still pretty good. Very good, in fact. I don't see any Cook's D's greater than 1, so there's no undue outliers or influencers here. And I got a Durbin-Watson of 1.5. So far, so good. So my candidate set of drivers now for the best model selection is going to be between these. Okay, so now that we've found a set of variables that VIFs, that multicollinear is not a problem, what we're going to do is now use a process to find the best model. And there's a couple of different ways to do this, but essentially the standard way to approach this is just to look at every possible combination of independent variables. So Megastat has a feature to allow you to do this. It's called the best model, or all possible regressions. And what it's going to do is one by one drop out independent variables, and then it's going to start by dropping one independent, well, looking at all of them, then dropping out one, and then dropping out 2, and then dropping out 3, and it's going to show us the statistics for each one of those. And what we're going to look for are some things that have desirable characteristics, like one that has, high R squared and low standard error, and has all significant slope parameters. When we do have some flexibility in choosing what we call the best model. So we do want things that have a high R squared and a low standard error. But I mean, if the R squareds are both high, like if they're both in the zero 0.9 something, minor differences in R squared and minor differences in standard error aren't really going to make a difference to your forecasts very much. So really, you look for big differences, not small ones. And so you can always choose one thing over the other if they are fairly close and without having much of an impact, and you can sort of get more mileage. You could choose a simpler model or one that doesn't have problems with nonlinearity or has problems with some of the other assumptions of our model. We want to keep in mind that our p-values don't actually tell us so there's an overall p-value for the model, and then there's a p-value for each individual slope. And each individual slope's p-value really only tells us whether the slope is, how confident we are that the slope is not zero. So just having the lower p-values don't mean better. It just means more confident. And so you just need to be confident enough. So, if we have to fiddle around by sacrificing a little bit of p-value or R squared or standard error, it's okay. So let's go ahead and do that. How do we do that? So what we're going to do is go do another regression, but this time we're going to do all possible regressions. So we go to regression analysis, keep everything the same, and we're just going to click here, all possible regressions. There's another thing called stepwise regressions, which is kind of similar, but we'll just do all possible regressions. And you notice that everything blanks out because you'll see that it provides a report of all the different combinations of things. So what we have here is a table that shows all the different combinations of driver variables. And at the very top, now Megastat tries to order it by what it thinks is the best in terms of what has the smallest standard error, the highest adjusted R squared, and maybe the lowest p-value. Because these things actually can kind of compete with each other, there is something called the CP or the Mallows statistic, and not all versions of Megastat will do this. On the Windows, I believe on the Mac, you won't get a CP. Don't worry about it. It's just a tool. It's a tool that allows you to more conveniently sort of see which one has the best combination of things. And the Mallows statistic basically says that you've got a pretty good candidate model if the value of the Mallows statistic is equal to the number of variables in the model. So in this case, that's what the p here. P is the number of variables. In this case, we have a Mallows statistic of 2.838. And what we want to see is that that's very close to the number of variables. Now, the number of variables in this model is going to be determined by which box here has p-values in it. So there's this one, and this one. There's also, it says NVAR, which is the number of variables, which is 3. So actually p equals 3 here. So we see that 2.83 is pretty close to 3. And so that indicates that this is probably a pretty good model, at least according to the Mallows statistic. And the other way of looking at it is you see that this has a low standard error, a high adjusted R square, and a very low overall fit. The other thing we want to take a look at is the individual slope coefficients. Now, for reliability purposes, we'd like to have each one of these guys to have a slope that's fairly confidently not zero. And when it's yellow like this, we know that it's at least 0.05 significance not zero. So the slope not being zero at a level of significance 0.05, otherwise, in other words, we're at least 95% confident that the slope is not zero. We see that this coefficient for gasoline is actually higher than 0.05, so that we are not that confident that the slope for this is not zero. So if we have our choice, we want all slopes to have high confidence that it's not equal to zero. Now, what we want to do is if you have the Mallows statistic, then you can look at the absolute value of CP minus P, okay, and that's going to be, see if I accept equals, not like that. If I go over here and say equals the absolute value of CP minus P, like that, That's going to tell us how close the CP is to P, the number of variables. So I can go ahead and get all of those. And so the closer to 0 it is, the better. And you can see that these are roughly smallest to highest. And you might find occasional things that are flipped around, but generally speaking, it's going to be lowest to highest because that's what Megastat did. It sort of ordered them according to the lowest standard error and the highest adjusted R squared, etc. The other thing we want to look at is we want to see whether the slopes are significant, have significant coefficients, all significant coefficients. So you can kind of eyeball it, and you can see that this one doesn't because this one's missing, and this one has only 2 variables, and it does. All of them are significant, but this one doesn't. It's kind of hard to eyeball it, so I have a little formula that you could use if you want. So I'm going to go back and grab this formula here. All it does is just look to see which things have all significant coefficients. So I'm just going to go paste that into here. And it says the predictor range. So I'm just going to delete that. And the predictor range is all these things here, like that. And you see that it will put an OK if all of them are significant. So my first candidate model that has a good CP minus P, a low CP minus P, is this guy right here, and has all significant coefficients. And the next best one seems to be down here and has a significantly higher CP minus P. So this is probably the best one to look at right away. And notice it only has 2 variables, which is nice. So what I'm going to go do is I'm going to try running my regression with that, and I'm going to do a holdout test. So I'm going to start out by seeing if this is a good model, and I'm going to validate that not only by looking at whether it has meets all the assumptions, but I'm going to do a holdout test. The first thing I want to do is let's just run the regression with it and see what the line assumptions look like, just to make sure I'm not running into any trouble with that. So going back to here, and I should take a look at what the model I'm looking at. I'm looking at prime lending rate and Medicare quality. So it's these 2, prime lending rate and Medicare quarterly expenditures. So I'm going to take everything out but those. And pasting that there like so. And deleting those columns there. Oh, where's my prime lending rate? I took that out. Whoops, by accident. I didn't mean to do that. Cut. And paste that back there. And let's go and just insert columns to get that out of there. Okay. Megastat. And correlation regression analysis. Okay, go grab my 2 variables here only. And I'm not going to bother doing predictors and stuff yet, but I'm going to take it off of all possible regressions. I know that the VIFs are going to be okay, so I don't need to look at that anymore. But I do want to output everything on this side, all the residual analysis, to make sure that my assumptions look okay. So go ahead and do that. And you don't have to do this one first, but the one thing I already know what the adjusted R squared is because that was in my all possible regressions. So when I was already looking at my all possible regressions here, you see, I already knew that the adjusted R square was going to be high, 0.968, and it's got a low standard error right there. So I don't really have to look at that again. I don't need to look at the VIFs. I know that these are significant because I already saw that from the all possible regressions. See, those are the same ones here. And I don't see any influences or outliers, which I know is good. What I do notice is that the Durbin-Watson is less than 1.3, and I do see a snaky pattern here for the residuals. That's not good. And so I might want to reconsider using this model. Or I'm going to have to do something to fix this Durbin-Watson, either add a mode or add another variable that's not correlated with this much. That's not going to change things. I'm looking at the residuals by predicted, And I don't really particularly see a wedge pattern, but if you're concerned about the wedge pattern, you can take a look and see, take a look at the residuals by taking the predicted here, right, and putting it over here like that. And then I'm going to look at the absolute value of the residuals, which is going to be equal to absolute value of that. Okay, and then I can pop those down. So this is just the absolute values of these. And then I can just give myself a little insert here, insert a scatter plot there. And there's the absolute value of the residuals. And now I'm going to just plot a linear trend line on that. Put an R squared. And I see that I get an R squared that's not nicely below 0.2. And so I'm okay. So this goes with this. No wedge pattern. Nothing greater than 0.2 on that absolute value of the residual. So that's okay. So this is the equal variances one, and this is going to be the linearity for a monthly quarter. Again, I don't see any smile or frown patterns, but if you're concerned, you want to double check, you can kind of add a trend line. And this time I'm going to add a polynomial trend line with an R squared there. And I see that I don't get an R squared of greater than 0.2, so I'm okay there. And prime lending rate, again, linearity. If I'm concerned about that, I can add a trend line and do a polynomial trend line here. And I see once again that I get it below 0.2, so I'm okay there. This looks reasonably straight, but if I'm, again, worried about this, I'll just calculate the skew and the kurtosis. And so the skew and the kurtosis is just go to the residuals. So we'll keep the skew of the residuals here. Now this time I want the residuals, not the absolute value of the residuals, but the residuals, and get the kurtosis of this. You could run descriptive statistics if you want on it, or you could just do it one by one like I'm doing here. And I see the skews, kurtosis, both -1 and 1. I'm okay. Plus I have 28 data points, so it's pretty good. So the assumptions all look good. The only thing that's bad is the assumption of independence of errors, and we do have time series data, so we have a low Durbin-Watson. This is something we're going to have to deal with. So everything looks really good except for that. What do I do with it? Well, how do I fix this? So this model looks very, very good except for my Durbin-Watson. Well, one option is to take a random subset of the data, and that would remove it from having the problem of being time series data. The problem with that is that I don't have that many data points. I have 26 data points. So I would have to remove about a quarter or a third of this to bring that Durbin-Watson back up. And that, because I have less data, it's actually going to increase my standard error. So that's probably not a good idea unless I have more data. So what can I do? Not quite sure. I could add another variable in that is not that correlated, or I could try to account for the modes. Now, I'm just going to keep that in mind for right now. Before I start trying to fix the Durbin-Watson, I want to see if this model is actually good enough to predict its own data. So that's going to be called a holdout. So this is the validation with a holdout, is that what I'm going to do is leave out the last 2 data points, and then I'm going to run the regression and try to use that regression to predict the 2 values that I left out. And if the model that with that less data can predict the 2 points that I left out within the 95% prediction intervals, then I'm going to say that that model is valid. So if it wasn't able to do that, I would be questioning whether that model is very good. So even though a 95% prediction intervals only should have an error 5% of the time. So if I, it would be unusual for it to have even one error, and certainly if it had two, not error, but not being able to predict it once. If it wasn't able to predict it twice, that would definitely be questionable. Okay, so let's take a look at that. And the reason why we do this holdout test is we want to make sure that it wasn't just sort of by accident that the data was happened to fit it really well. So we go back to our data, and what we're going to do is we're going to hold out these two. So I'm just going to color those green like that, and I'm going to go to Megastat and do regression analysis. And I leave the input range the same, but the dependent variable is now going to be actually I need, well, the dependent variable, I need to go down just to the Q4 2011, and the independent variables, of course, I'm going to have to cut out those ones too, so I don't just go right to here like so. So I'm just getting, so leaving all this out here. And now I want to predict it. So I want to predict it. I want to predict these. I assume that I don't have them using those. Okay, and it's good to get all this stuff too. You want to see that it's not violating any of the assumptions by the holdout test. Okay, still got a pretty good R squared and good p-value and everything's significant. No influences or outliers. Well, there's this one, but it's not greater than 1, so that's okay. Here's our predictions. These are the predictions that it's made, and here are the prediction intervals. So I'm going to write actual here, and in prediction interval, yes or no. So my actuals, so go back to my data, these two guys. And I see here's 89.95 million. And is that in between the lower and upper prediction interval? Yes, it is. See, 77 to 97, 89 is right in between. So yes. And how about this one here? 86.89 is between 83 and 106. And yes, so both of them are, both the prediction value, the actuals do fall within the prediction intervals here. So in terms of the holdout validation, this model is valid, at least for predicting that. I notice that my Durbin-Watson still pretty low. That's a little scary. And what actually that does is actually gives us a lower standard error, which would actually make it more difficult to get into the prediction intervals. So I'm not too worried about that. The residuals by predicted, again, the equivariance is still probably okay. If you want, you can redo the wedge test, but it's probably okay. I don't see any pattern here or here, and that doesn't look much different. But if you're worried about it, you can run the skewness or kurtosis. But the line assumptions all look okay, except for the Durbin-Watson. And as I pointed out, that's only going to make things harder to predict. So I'm going to say this passes the validation test, the holdout validation test. So because of that, the next step, this looks like a very good candidate model, except for the fact that I have a Durbin-Watson problem. So that I've already checked all the assumptions for that, and I looked at the Cook's D, and I looked for influential outliers, and I didn't have any of that problem. So before I do my final forecast, let me see if I can figure out this Durbin-Watson problem. What I'm first going to do is go back and take a look at the predictions I had. Did I do predictions? Yes. Let's see. Well, let's see what we can do about this Durbin-Watson problem. Now, remember that we noted that there were some potential modes here. So let's just say we don't really know what might cause this, but let's just say that we want to notice that we want to take into account that down here, the revenue seemed to be in one mode, and then here it started to go to another mode, and then here maybe another mode. So I'm going to create something, I might investigate why later, that this is 0.9. At 0.9 something happened, and then again at 0.19 something happened. So 9 and 19. So 9 and 19, 0.9 here is quarter 1 of 2009, and 19 is quarter 3, 2011. So I'm going to put a mode in there, and the way I'm going to do that is add a new variable to my data. So let's just do an insert here, and I'll just call it mode. And so all the way, I'm going to say that nothing happened up until quarter, so 1, 2, all the way up to 9, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, or quarter 1, 2008. Is that right? Let's go double check that. So we're saying right here 0.9, it's quarter 1, 2009. Quarter 1, 2009, so let's go back to that. Okay, quarter 1, 2009. Nothing happened. And then after that, all of a sudden something happened, all the way to 19. So we're going to say like over here, something started to happen again at 20. So 20 is quarter 4, 2011. And then we're back to 0 again. Okie dokie, so we will now do our regression with this new variable that's taking into account this mode, even though we don't know what it is. And we're going to say that we have all that stuff there, and we want to use this stuff to predict these things here. And we're going to get our good things here. Whoops. Oh, that's got to be to D27. Yes, that's right. Okay. Okay. Again, not surprising that these are all going to remain the same. Looking at my Durbin-Watson, hey, it actually improved to 1.28, not too shabby. So it's pretty close. You might just say that's good enough, and we'll go for it. And these are our predictions here. Or if you don't like that, you can try a different attack to improve your Durbin-Watson and maybe get it even higher. Again, taking a look at these things just to make sure you didn't introduce any nonlinearities or anything like that. So adding this mode may help. As you saw, it did help with the Durbin-Watson. You might want to go back and try to figure out if there was anything there to explain that mode. But it's okay, actually, just to leave it in there, even if it's unexplained. Let's try a different one just for fun. Let's instead of adding in a mode, let's go add in something that's not terribly correlated. Now, as I recall, going back to the all possible regressions here, we actually had some good models that so we use this model here. That's where we're at. But the one above it was also very, very close. It's very, very good. In fact, even slightly better. The only problem with it is it had this thing called gasoline regular grade retail price taxes that didn't have a significant slope. So what happens if we add that in? Well, it may not be a good predictor, but it actually may help with that Durbin-Watson. It may help counter this autocorrelation problem, so long as this guy isn't too correlated with everything else. So let's go look at the correlation for gasoline. Where is gasoline? Here it is, retail price gasoline. And it really isn't highly correlated with anything. So it's not correlated with revenues, so it's not going to really contribute much. But it's also not terribly correlated with the things that we have in our model. So here, let's take a look at this one. Yeah, this is the one. It doesn't have anything. Again, it's not correlated, highly correlated with anything in our model. So this is gasoline. It's right here. So if we added that in, let's see what effect that has. So adding that back in, where's gasoline? Here's gasoline. Copy that. And I'm just going to paste it over my mode. I can always put that back if I want. And for convenience, I'm just going to rerun my regression. There it is. Same, everything's the same. Just run it because I wrote over the other one. And everything looks pretty good. I got a Durbin-Watson that's even better, 1.38. So because I have a Durbin-Watson of 1.38, that is definitely within safe territory. And I can look at what my predictions were. Here's the predicted values. And I can compare the predicted values with the ones up here from the previous candidate model with the mode. And you can see they're not terribly far off, right? Not terribly far off. They're almost the same. So why don't we go ahead and use these ones here. So we're going to use this model. So we're going to use the model that actually added it in there. And there is our predictions. It's always a nice touch to when you're writing up your report to actually show what the forecast is. So you can always just take this data, showing meaning like visualize it. So you can paste it here like so, and you can just take those and cut them, paste it here, and you can introduce it like that, and you can do a insert line chart like so. And you can see there's a significant drop here. So this is what our forecast is in red. Now, since this is past data, we could actually go what the actuals are and see what they were. And it actually turns out that they kind of follow the regular trend here. This drop here was due to, if you go look over here, it has to do with the Medicare expenditures. So it was 27 billion here, 27 billion here, and all of a sudden it dropped to 21. And then 22. So it had a kind of a big drop in the forecast here. That actually didn't occur. So remember, your forecasts are only going to be as good as the forecasts of your independent variables. Okay, so there you have it. That's more or less everything in a nutshell. You can go see a more complete example by going to the Almost Family Home Forecasting Project. Again, you have plenty of variability or options in how you do things. So good luck with your FP3.